Okay, welcome to Unit 2.1b, Solutions Chemistry Notes video, Part 2 of 3. Alright, so in the last video, we looked at different types of electrolytes, some that completely ionize and some that do not. And remember, for salts, the ionization depends on the solubility. So we have an example here with sodium chloride where you can tell that's completely dissolved. It looks like all one thing. And then for silver chloride, it's not. And the way that we sort of denote that is we utilize these double arrows to tell someone who's looking at it that, hey, it doesn't completely ionize, doesn't completely dissolve. Some of it will remain as solid. And for acids and bases, ionization depends on their strength. So strong acids and bases will completely ionize, so we use these single arrows to represent that, and then weak acids and bases will not, so we'll use these double arrows. All right, so sort of like to summarize the representations. Again, for cases where it completely ionizes, we use the single arrows, and then for where it does not, we use the double arrows. But what about for particle diagrams? We actually draw a particle diagram to sort of visualize what's happening. If it completely ionizes on the product side, everything should be broken down into ions because it completely ionizes. However, for things that do not completely ionize, you should show some things broken down into ions, so you should have some ions, but you should also have some of the original molecules as well. And even though they'll be aqueous, the solution will be aqueous, they will not be ions. Okay, so we're going to take a look in this video about how to create these sort of like particle diagrams. Let's say, for example, you were asked to show the ionization of 3 moles of magnesium nitrate. Now, this is a nitrate salt, so remember from our solubility rules, all nitrates are soluble. So we're going to use a single arrow here because we are saying it completely ionizes. So just to begin with, for our starting compound, we're going to draw this sort of, we can draw the particle diagram with the cation in the middle here, and then it's 2 anions with their respective charges. And then for the products, we can split apart everything into their ions. One quick note, it's important when you're doing the reactant and product side to follow the law of conservation of mass. So the number of cations, we have 1, 2, 3 magnesium cations, should match that on both sides, 3. And there's 6 anions, and again, there's 6. Okay, so instead of drawing out the particles, another way we can draw it is just by writing the molecules on the left side for the reactants, and then on the product side writing out all the ions. And it sort of shows the same things. And once again, we make sure that everything matches up. We have 3 magnesiums on both sides and 6 nitrates on both sides. All right, let's look at a case for a salt that's insoluble. So you take something like lead chloride. So remember, most chlorides are soluble with the exception of the leads, the silver, and the dimercury. All right, so we have lead chloride and all together, but then when we dissolve it, since it does not completely ionize, as we indicated here by these double arrows, we're still going to have some of it in its molecular form. And I chose to keep 2 of them as molecules and then split one of them apart. Now, the number of them that you draw as molecules, the number that you split apart, sort of outside the scope of this video, but later we're going to learn about something called Ksp values, which helps you know like how much of it, relatively how much of it will ionize and how much of it will not. Of course, these ratios will never be perfect, but I have the understanding that most of it will not ionize, so most of it will stay like this. So that's how I chose 2 out of 3 to stay like as a molecule and only ionize 1 of them. Okay, so that's drawing in a particle diagram, and then once again, of course, we can draw it this way. So with this, we kept the molecule as PbCl2, and again, they told me I had 3 moles of them, so I drew 3 of them. And then on this side, I need to have the same number of things, but I only chose to ionize 1 here. And so the 1 PbCl2 breaks up apart into a lead ion and then 2 chloride ions. And here you may be wondering, well, what is this? For salts, it's also helpful to draw sort of like a line to sort of demarcate the solid, which will settle at the bottom. So this is like, this line is showing me that here is where my solid is. And at the top here, we have this solution. And so that's what I'm drawing here. I'm showing there's like a big clump of lead chloride, and I just put the molecules here. So that's something you may see for insoluble and soluble salts. We don't do that sort of thing for acids and bases because typically acids and bases are not going to clump up into the solid. Okay, so let's look at strong acids. So again, same sort of thing. We start off with HI, and since it's a strong acid, it's one of our list of strong acids there. It's going to completely ionize, so we use a single arrow here, and then in the particle diagram, we split everything up into its ions. There are no molecules left. We can do it, of course, using the molecular or chemical formulas. Here, they tell me I have 3 moles of HI, so I do 3 of those, and then I split it up into its respective ions. Remember, you want to make sure that both sides have the same thing, same number of hydrogens, same number of iodines. And also, you also want to keep track of your charges to make sure that they are correct. Okay, let's take a look at an example of a weak acid. Instead of just showing the particle diagram, I'm just going to show them the chemical formula way of doing it because I think that this is easier and this is the way we're going to do it moving forward in this video. So HNO2, they tell me I have 3 moles of, that should say HNO2 by the way, so please make that correction. 3 moles of HNO2, 1, 2, 3. And since it's a weak acid, this is nitrous acid, I'm only splitting up 1 of them and keeping 2 as whole molecules. So the main difference is when it's a strong acid or strong base or a soluble salt, everything should be an ion, and when it's a weak acid, weak base, or an insoluble salt, some of it has to remain as a molecule. Okay. All right, so it's sort of your turn to sort of try this out. You're going to draw a model, and I would recommend you use the molecular formulas for 4 moles. If you go back up here, you'll see it says 3 moles of HI. So I should say 3 moles of HNO2. I have 3 moles of these, 1, 2, 3. So basically each molecule would represent a mole. And even though one molecule is not a mole, but just for the purpose of the model. So here you're going to have to start off with 4 of each of these things. And then based on your understanding of its strong acid, base, or a soluble salt, or if it's a weak electrolyte, you're going to have to depict the products appropriately. All right, so you have several spaces to do this in. So when you are done, the answers will be revealed. Okay, so let's take a look at 3A here. Here's the work for 3A, so take a look. You want to make sure that you have the right number of things on both sides. Everything matches up. You have 4 strontiums and 8 hydroxides on both sides. And of course, the charges should be correct, and everything should be split up because it's a strong base. Here, this is a strong, this is a soluble salt. It's a group 1 salt, so it's completely soluble. So everything also is split up. Here it's a strong acid. Once again, everything is split up. So you want to check that and also check your numbers. For this one, we have a weak base. So NH3 is a weak base. And because it's NH3, we also have to show the H2O as well. It's a little bit of a trick. Because remember, when it's a Bronsted-Lowry base and not arrhenius. So NH3 is not going to split apart into ions. It gets the ions by reacting with water. And we saw that in 2.1a. And at any rate, because it's weak, not all of it is going to sort of react with the water and form the OH minus. So I'm showing some of it has reacted with water, form OH minus, but I showed 3 of them as whole NH3s. And I also showed the 3 water molecules as well, just to keep things balanced. Okay, here we have a insoluble salt. So for that silver bromide, I just drew this sort of line here to indicate that this is a solid settling at the bottom. And here we have in the solution above it the bromide and silver ions. And so because this is weak, once again, only some of it will split apart into ions and the rest should stay as whole molecules. Okay, silver nitrate is soluble, and we know that because it has a nitrate, and all nitrates are soluble, so everything breaks apart. So you want to make sure everything matches up, same number of things on both sides. Okay, the last one, we have a weak acid. This is one of the carboxylic acids or Ku group acids, and so I only showed one in this case, one sort of splitting up. And here we have the rest of them just as whole molecules. You may have chosen to do 2 split up into ions and 2 whole molecules. That's totally fine. All right. The key things are that if it's a weak electrolyte, meaning it doesn't completely ionize, then you need to have some of it as molecules on the product side and some of it as ions on the product side. Okay, we are going to stop this video here, and then the last video, part 3, when you're ready, you can press play on that. Have a quality day, folks.